If you've ever tried to teach a dog a new trick, you know that timing is everything. If you reward them a second too early or a second too late, the dog gets completely confused about what exactly they did right. To teach a complex action, you have to provide that reward at the exact right moment. It's the only way a biological brain connects a specific movement to a successful result. When we apply this exact same logic to machines, it's called reinforcement learning. It's essentially the same process, just applied to motors and sensors instead of muscles and paws. In the digital world, those treats are actually mathematical points buried in the robot's code. Robots don't have feelings, but they are driven by a single goal: collect as many of these digital points as possible. But teaching a robot to move is incredibly difficult. Take pen spinning, for example. It requires so much coordination that even the most advanced robotic hands usually end up fumbling and dropping it. The problem is the math. A human programmer has to decide exactly how many points to award for a tiny pinky twitch or a specific wrist angle. It's nearly impossible to get those numbers perfect. Right now, scientists mostly rely on expert guessing. They manually tweak these equations over and over, testing one idea at a time to see if the robot gets any better. Because humans simply can't write these reward rules fast enough, our own manual coding has become the biggest obstacle preventing robots from moving with real skill. To solve this, researchers created an AI called Eureka. It's built on the same language technology as ChatGPT, but it was designed to function as an automated trainer for robots. This diagram shows the system starting. We feed Eureka the simulation's digital rules, teaching the AI boundaries like gravity and joint movement. Eureka builds its own understanding of physics just by reading the raw instructions of the virtual world. Once the AI maps out the environment, the training process shifts from human guesswork to high-speed digital logic. Where a human expert might test one new idea a day, Eureka can generate 16 different point systems all at the same time. It sets up 16 simulated robots and gives each one a different set of rules. Then it runs the training in fast forward to see which point system actually helps the robots learn. In the beginning, it's a mess. Most of these attempts fail spectacularly, with virtual robots falling over or dropping objects immediately. But those failures are actually useful data. They allow Eureka to see exactly which mathematical rules lead to success and which ones cause the robot to fumble. This is where Eureka's real innovation comes in, a process called reward reflection. Essentially, the AI writes its own performance review for the code it just created. For example, if a robot drops an object, Eureka might realize that its rules were rewarding the robot for moving too fast rather than rewarding it for holding on tight. This Python code shows Eureka rewriting itself. The red line deletes faulty math, and the green line adds improved numbers. It repeats this loop over and over, testing, reflecting, and rewriting the code to be slightly better next round. By letting the AI critique its own logic, we completely remove the human bottleneck from the training process. What used to take human experts months of trial and error, Eureka can now figure out in just a few minutes. This graph shows the results. The red dashed line is the success rate of human-designed rules. The blue line shows Eureka's rules climbing much higher as the AI evolves. When tested across 29 challenges, Eureka's rules beat human-engineered ones 83% of the time. This variety shows that the AI isn't just good at one specific task. It can apply its training logic to 10 different types of robots, ranging from four-legged walkers to complex mechanical arms. This marks a change in how we approach robotics. Instead of humans coding every specific movement, we can now use AI to solve the most difficult problems for us. The clearest proof of this is the pen spinning challenge, a trick so dynamic that human programmers had never successfully coded a robot to do it. This graph tracks how many times the robot can spin the pen in the circle. The flat lines at the bottom show standard methods failing, but look at the blue line. It rockets upward as Eureka perfects the movement. Here is the result. For the first time, a robotic hand can spin a pen around its fingers in a rapid, continuous loop. We no longer need to spend years manually coding the way a robot moves. We can simply tell the AI what the goal is and let the machine become its own master trainer.